Hey everyone, welcome to Science Giga. In this video, we will discuss about the ground state of hydrogen atom by using variational method. In previous videos, we have done the basics of variational method. Then we did the ground state of helium atom, and also we have done the 0 point energy of harmonic oscillator. So by using variational method, we will do this last problem, which is the ground state of hydrogen atom. Now we know the basic steps which are followed in variational method. That is, first we choose a trial wave function, then we choose a Hamiltonian according to the kinetic energy and the potential energy. Then we also choose a variational parameter, and then we find the expectation value of the Hamiltonian and we minimize it with respect to variational parameter and put it equal to 0. Then on solving those equations, we come to a conclusion of the ground state energy or the ground state wave function. Similarly, in this problem, we will find the ground state of hydrogen atom. Now we know that a hydrogen atom consists of a positively charged nucleus in which there is one proton and one electron, and this electron circulates around the nucleus in a stationary orbit. So this is the basic thing which every one of us know. So now we will find the trial wave function of hydrogen atom. We actually assume the trial wave function of the hydrogen atom to be a psi 1s equal to a e raised to a minus beta r, where 1s is the ground state of hydrogen atom. So equation 1 will give us the trial wave function of hydrogen atom, in which a is a normalization constant and beta is the variational parameter. Now since we have used here r coordinates, so we can say that we will use the spherical polar coordinates here. So the volume element d tau will be equal to r square dr sine theta d theta d phi, which is the volume element of a spherical polar coordinate. Now we know that this wave function will satisfy some conditions, which one of them is the normalization condition. So we know that the normalization condition is integration psi star psi d tau is equal to 1. So this is the condition which is to be satisfied by our trial wave function. So by putting the values of psi and psi star in this equation, we will find out the value of the normalization constant a. And since we are using spherical polar coordinates, so we know that the limit of r goes from 0 to infinity, the limit of theta goes from 0 to pi, and the limit of limit of phi phase angle goes from 0 to 2 pi. So we know that this psi does not contain any iota term, so psi star and psi, that is psi 1s star and psi 1s, will be equal. So we get this equation number 2. This part is the psi, and this is the psi star and this is psi, and this is the volume element, which is r square dr sine theta d theta d phi, and we put this integral equal to 1 according to normalization condition. Now we separate out the r term and theta and the phi term, so we get this equation. Then we will use a standard integral, and this integral will give us cos theta, because integration of sine theta is minus of cos theta and its limits will go from 0 to pi, and this integral will give us the value 2 pi, because when we will integrate d phi, then we will get phi, and whose integration limits will be from 0 to 2 pi. So on whole, when we will solve it, we will get the value 2 pi. Now this part of this integral will be solved by the standard integral, which is given by this equation number 3. So you can see here that whatever I've explained earlier, it is given here. That is integration of sine theta is minus cos theta, and the limits will be from 0 to pi, and integration of d phi will give us 2 pi. Now By using this standard integral equation number 3, we will solve this term. Here we know that the n is 2, n is equal to 2. So when we will put this value of n in this equation number 3, we will get 2 factorial upon, here alpha is minus 2 here alpha is 2 beta, so we will get 2 beta raised to power 2 plus 1 is 3. So we will get this equation. Now on solving this equation, we will get the value of a, which is equal to beta raised to power 3 by 2 upon under root pi, and we name it as equation number 4. Now we assume that the nucleus is at rest, only the electrons are revolving there. So our Hamiltonian will take the form which is shown here, that is H will be equal to kinetic energy plus potential energy, where we know that kinetic energy is equal to p square by 2m, and potential energy is given by minus E square by r. So we know that momentum operator is given by h cut upon iota del, and if we square it, so we will get p square equal to minus h cut square del square. So since we are interested in only radial part of the momentum operator, we will get p r square is equal to minus h cut square del r square. We have used only radial part because our wave function consists of only r term, so that's why we will use radial part of momentum operator only. And we know that this del r square is the Laplacian operator, radial part of Laplacian operator, and we know that the radial part of Laplacian operator is given by 1 upon r square curl by curl r into r square curl by curl r. So we will put this radial part of Laplacian operator in this equation. So we will get the p r square term equal to minus h cut square upon r square curl by curl r into r square curl by curl r. So the radial part of Hamiltonian will be given by this equation. We will put this p r square term here. So we will get h equal to minus of h cut square by 2m into 1 upon r square curl by curl r into r square curl by curl r, and this is the potential term which is already mentioned here. So now we want h of psi. So we will multiply psi on both sides, where the value of psi is a into e raised by minus beta r. Now we will multiply this wave function in every term in the bracket. So we will get h psi equal to minus of h cut square by 2m 1 upon r square into curl by curl r into curl r square into curl by curl r of a e raised by minus beta r minus of e square by r a e raised by minus beta r. Now we will multiply this term inside the bracket. So we will get curl by curl r of a e raised to power minus beta r. When we will differentiate this wave function, we will get a in minus of a into beta e raised by minus beta r, because a is the constant. We will differentiate this term with respect to r, so this e raised by minus beta r will give e raised by minus beta r into, now this term will also get differentiated, so we get minus beta common in this term. So now this part is solved. Now we are left with r square into this term, and rest whole term remains the same. Now we will differentiate these two terms, that is r square into minus of a beta e raised by minus beta r with respect to r. We will use uv rule here, that is curl by curl r of u into v will give u v dash plus v dash u. So by using this this rule, we will differentiate these two terms and we will get the result which is given here. Now on solving further and arranging the terms, we will get the value of h psi as this And on further solving this step, we will get value of h psi, which is equal to minus h cut square beta square by 2m plus bracket h cut square beta by 2 minus e square into 1 upon r and into a e raised to minus beta r. So this is the value of h psi. By using this value of h psi, we can find the expectation value of energy. And we know that expectation value of energy is given by integration psi star h psi d tau. So this h psi will be used here and we will get the expectation value of energy. Now again we will use the spherical coordinates. So the d tau will be equal to r square dr sine theta d theta d phi, and we will set the limits of r as 0 to infinity, limits of theta will be 0 to pi, and limits of phi will be 0 to 2 pi. And we know that psi star and psi star is equal to a raised to power minus a into e raised to power minus beta r, and this is the h psi term, this whole term is the h psi term. And here we will simply solve the we will separate out the r terms, and then we will separate out the theta term, and we will separate out the phi term. This phi term will give us the value 2 pi. This 0 to pi theta term will give us the value 2. So this phi and theta term will give us the value 4 pi. Now we will put the value of a square using equation 4. So the value of a square will be beta cube upon pi. We will put this value here. Now we will just make the multiplication of these terms inside the bracket, and we will further solve the terms and arrange them so that we will come to this solution, and we will use the standard integrals which we have used earlier. And by using this standard integral, we will come to equation number 6, which gives us the expectation value of energy, which is h cut square beta square by 2m minus of beta e square. So here is the solution of this expectation value. You can copy from here and you can understand from this, because here only the multiplication thing is done and only the arrangement of the terms is done. So now we need the minimum value of the expectation value. So for this we know that we will differentiate the expectation value of energy with respect to the variational parameter. Here the variational parameter is beta, so we will differentiate this equation number 6 with respect to beta. So when we will differentiate it, we will get the term which is given here, that is h cut square by 2m into 2 beta, because here we have E is expectation value of E equal to h cut square beta square by 2m. When we will differentiate this term, we will get h cut square by 2m, and differentiation of beta square will be 2 beta, and in second term we have minus of beta E square, which will give us the value E square. So we are left with this term. Now because we have put this equation equal to 0, so from here we can find the beta equal to 1 upon a naught, where a naught is the Bohr's radius. Here value of a naught is equal to h cut square upon m e square. This a naught comes as when we will solve this term, we will get h cut square upon 2m into 2 beta equal to e square. This 2 will get cancelled with this, so beta will be equal to e square into m upon h cut square. So from here we have used beta equal to 1 upon a naught. So from here we can say that a naught is equal to h cut square upon m e square. So the value of a naught is h cut square upon m e square, whose numerical value is equal to 0.5267 angstrom. So when we will use this equation number 7 in equation number 6, we will get the minimum expectation value of energy. We will put the value of beta square here, value of beta here, and we will get the equation number 8, which will be the exact eigenvalue of hydrogen atom in ground state. That is, we have come to a conclusion that minimum expectation value of energy of the hydrogen atom for the ground state is equal to minus E square by 2a naught. Now corresponding to this eigenvalue, we have the wave function psi 1s equal to, we have used the trial wave function psi 1s equal to a e raised to power minus of beta r. Now we will put the value of a and beta in this trial wave function, and we will get the exact eigenfunction of hydrogen atom which will be given by equation number 9. So this was the result which was required to be concluded in this video. Now this will be the last problem for the variational method, that is the application of, this will be the last application of the variational method, which was the ground state of hydrogen atom. That is, we have found the ground state of we have found the ground state of hydrogen atom by using the variational method. I hope you've understood the topic. For more interesting videos, please hit the like button and subscribe the channel. Thank you.